This is kind of a technical name for speed sensors. So one of the things, of course, we need to sense is how fast things are moving. The book we used to teach out there referred to it as angular velocity sensors, but these are speed sensors. In fact, that's what I need to do. I need to change the name for this class. Of course, this is a recap. Of course, I don't think I had. Was this on the test? Should have been.
I don't know what on the test.
Yeah, it should have been on the test. So we'll make sure this gets. Now this. Of course, we went through all the dish. We looked at position. We looked at. We don't see proximity up here, but what we're looking at now is speed, right? And of course, the different types of speed sensors we have is what we call tachometers. And we'll look at what we call tooth rotary tacks, and we'll look at direct current tacks and AC. So most of y'all feel that. A lot of the cars have tachometers or tacks as part of a lot of it's standard equipment now where they actually put a tack up there, which don't mean much if you're using an automatic transmission. But it used to mean a lot if you drove a straight shift. So we have tacks that we can use on motors. And one of the tacks we use to get the speed of the motor is that we put a little reflective tape on the shaft of the motor, and then all we have to do is, so this is kind of like an incremental curve. That's exactly what it's like. But we usually only have one strip of tape, and we point the tack at the tape. It reflects the light back when it comes around, or gets real good reflection back, and then the piece of instrument does that to give us the speed. And this is pretty important, of course, if you got a speed control system, because a lot of times we need to verify the speed that the system's supposed to be regulating at, right? So this is very popular. But this is the first one. This is what they call a tooth. I gotta go back and look. Tooth rotor type. This is used a lot. So what we have is nothing but a magnet, and wrapped around the magnet we have a coil wire. And what happens is that each one of these tubes of the gear, when it comes up, it's a lot closer to the magnet, and so it would concentrate the magnetic field a lot. Then when it goes into the gap, then it would have less concentration. So what happens, it causes this magnetic flux to either be stronger, less, stronger, less, stronger, less, stronger, less. And what we need to do to induce a voltage into this conductor is we got to have a couple things. We got to have a magnetic field. And there it is, check. Right, you understand that. And number two, we need to have a conductor. Check. So the third thing we need to do is we need to have motion, which means the magnetic field has got to move. Well, you can see what's happening with this tube rotary tachometer is that every time one of those gear tubes come around, it's going to create more flux. When it gets in the valley, it's going to create less. So what we'd be getting out of this thing is we'd get these little old pulses that would represent every time a tooth came out. And then, of course, we could relate this to distance. So we'd have to know the number of teeth that's in one revolution, right? And then we could use that to convert that into revolutions per minute. Very accurate, very simple setup. Sensors can work in extremely harsh environments. So it's more likely that this is the sensor they use in your transmission to sense the speed right here than a Hall effect. Because this would give us a more precise speed, right? Because we got multiple teeth per revolution. If we only had one little magnet per revolution, then that's what we would sense is just that one magnet. Here we can sense all the teeth on that gear. And basically all we need is a gear, a metal gear. And they don't have to, the whole gear itself doesn't be metal, you know, all this in here could be plastic as long as the teeth itself are metal. It's a very mature technology. It's been around a long time. Can operate in real high temperatures. Disadvantage, of course, is when it gets down real slow, what happens? Well, it changes the motion. So the motion is occurring a lot less, so that means the pulses would be a lot smaller. But it's okay on the car. The Bridgestone plant, the maximum speed limit inside the Bridgestone plant is 11 miles an hour. And guess what's not on the speedometer? Most speedometers move in 5s. And the Malibu, it did that. So he kind of had to guesstimate at 11 miles an hour. And of course, you can tell your car's speedometer works very poorly at very, very slow speeds. And the higher the speed you are, the more accurate it becomes. We had some SCR drives that basically used this feature right here, used a tooth rotary encoder. We didn't use the gear to drive a chain or something like that, but we did use it to sense the speed of the motor. And that's one of the things that got thrown away, by the way. We had two Seco drives. Variable looker pickup looks almost like a inductive pickup. You can't hardly tell them. Usually the face of these guys are going to be metal though, and like I said, they can operate at high temperatures. They're really, really reliable. Very simple. The technology has been around for years. This is one of the first speed encoders that I actually was involved in. And then, of course, now we have what we call DC tacks. These are nothing but little old permanent magnet DC motors. And so a way a permanent magnet DC motor works, of course, is that we have permanent magnets out here on the side. And then we spin a coil of wires inside there. And we switch them, by the way. So these guys, let's see if I can find them. These are not DC motors. What's really nice about DC generators, we can run DC motors as DC generators. So the first time I got involved with it was on a little Learjet. And they used a DC motor to start the plane, and then they switched it over to a generator to generate a power for the plane, which is pretty neat. What we have to do, though, the problem we have with DC tacks, of course, is that these guys have to be maintained if they let you. A lot of times these guys are considered disposable. So what we have to do is that the rotor is actually wound. So we have a rotor that's wound. And I'm just going to do it like this. And then, of course, we have a permanent magnet right out here. And so let's say this is a north and this is a south. Well, what would happen if I just pull my power off these things, as this thing swings, notice one time this one up here is going through a north pole, and when it swings around it's going to a south pole. So by default, these guys are going to generate AC. So how do we do that? Well, we let the generator switch itself, right? You understand? So what we come up here and we attach this to these segments that we call commutators. And then the brushes always ride on one side. That makes sense? So what happens is right now this is going to this one's going to that one. If it spins, then this will move up to this one, this will move down to that one. So what we're doing is we're letting the generator do what? Constantly switch the output. So the winding up here is always going to the North Pole, and the winding down here always sees the South Pole. That makes sense? So when we come up here and look at these things, and this would be true on the DC motor too. That's what makes a DC motor rotate. Let's see what camera comes up. This camera. Is that, of course, all we have is two wires coming off of it. And the polarity depends on the direction of the generator. But when you look in this section, this is really, really nice. You can see what we call the brushes. And these are the carbon impregnated. They have metal and carbon in there, and they're pretty solid. And then this comes down and hits the commutator. And what I want you to do when I pass this around is look at the commutator and actually see the individual segments on the commutator. Now, the more segments you have and the more windings you have on the rotor, the more it is pure DC. And so we have this one. I don't know how many segments it has, but if you look at a DC motor, it's got a lot of them. In fact, I do have a. By the way, on the DC motor, we call the rotating part is referred to as the armature, and the stationary. And I got to figure out how to do that. I got to start using that screencast-o-matic because this guy's leaving at the end of this month, right? So DC tacks are used a lot, especially in DC drives. So there's a constant need, especially in manufacturing, to control. A lot of times we've got to control the speed of the process, right? You understand that. Number 4 galvanizing line was where they actually put the zinc coating on the strip metal that they got from the tin mill. And when you go through that zinc vat, you had to go through that thing at a precise speed. So that means if it went through the vat at the precise speed, that means the whole line had to run at a precise speed. They'll use DC motors. The biggest advantage of DC motors is that we can precisely control the speed and the torque over whatever range we want to. So you can literally run a DC motor so fast it'll sling itself apart. So we had some 200 horsepower motors on the take-up end at the number 4 galvanizing line, and we had one that would sling itself apart every once in a while. And we had speed sensors that had a centrifugal switch on it, so if it tried to run too fast, it was supposed to cut it off. And also we had the tack generator, but for some reason that guy would swing itself apart. Huh? So all we have to do on this guy is just attach it somehow to the motor or the gear. You know, we could do a gear assembly anywhere down the line. We could attach it to something that gives us an indication of the speed. So what we would do is we would take the DC generator and then we would run this into our air amplifier, right? And then we would come up here and we'd set up a set voltage. So we say, okay, if you run it, so let's say 3 volts. Well, if it tried to go above 3 volts, then the air amplifier would slow it down. If it tried to go below 3 volts, the air amplifier would do what? Speed it up. And these guys are very, very reliable. They work great. I mean, these motors are run almost perfect speeds. Yeah, in fact, we got, I'll have to figure out how to set it up again. So we have a little setup right here that we're using, and we had it taped down, by the way. So what we have here, and we use this one to go through our separator interrupter that I showed you. But also what we would do is we would spin one of them, and we would use one of them. We use one of them as a generator, and we use one as a motor. And that's what we're saying. It's what's so a lot of that. So all we have them is we have them heat shrink together. So we can use one as a generator and the other one as a motor. And of course, we can also have this sticking out here. And what we have on this little setup here, I'll have to tell it it's kind of pulled apart. Is we have the optical interrupter right here. And so one way we run it is we put the motor up here, let it spin, and then we'll look at it at the oscilloscope, and we'll see not only can we use this to sense position, we can also use this to sense speed too. And this is the error amplifier right here. So what this little pot right here is for is this is where I set how fast I want the motor to run. And then of course it goes through the error amplifier, which is an operational amplifier. And of course this transistor right here is running the motor. So that means if it tries to slow down, it puts more voltage on the motor. If it tries to speed up, it puts less. Works really, really well over the range. So it's really neat because what we can do is we can hook up our optical interrupter, and then we can load the motor with our finger, and you'll see that the output of the optical interrupter stays about the same. So error amplifiers, there's more. A lot of times there's more to this. They have to come in and do a lot of times they'll sense overcurrent on the motors, and undercurrent and all this other kind of stuff to protect the motor. So a lot of speed regulating circuits have a lot to do with it than just an error amplifier, which is pretty simple. So we'll try to figure this thing out and see if we can make it run. So we have a device called operational amplifier, which works real well as an error amplifier. Now DC is okay, but DC, these guys are eventually going to go out because those brushes are going to eventually wear out, right? So what we have next, of course, so this DC one that I found these specs on right here, it's a linear. It's got a 2% deviation, so that would give you the error. A 2% deviation over the range is really, really good, right? Maximum peak-to-peak voltage is up to, I don't know why they call it peak-to-peak AC, because this is a DC tag. Maximum speed range is between what? 1 and 6,000 RPMs. And so these are all kind of DC tags. This right here has actually been taken apart. And these guys here are linear devices. And what does linear mean? Yeah, their output voltage varies in a straight line. And the linear devices are really, really good as far as regulation with. And like I said, all we got to do is attach this dang thing to something that's in motion. Now, if we run this into a computer, normally what we have to do is bring this into a to D converter. And what the A to D converter does is it takes a input and it converts it over to an equivalent binary number. Okay. 1, 2, 3, 4, 5, 6, 7, 8. So what this would do is this would allow us to take this and generate 256 different numbers. So an 8-bit A to D converter, you get 256. 10 bits, you'd get 1,024. So the more digits you add to the A to D converter, the more accurate it would be. So what we're saying is that if the maximum this would put out, if it was 1,000 RPM, it put out 3 volts. Then what we could do is we could calculate the transfer function, right? So the volts would be what? 3. The RPM would be what? 1,000. So now we get volts per RPM. That makes sense? Now this is not going to give us this is not going to give us a weighted number. So what we're saying, when this thing here is running at 2,000 RPM, I'm not going to get the number 2,000 on here. I'm going to take this right here and divide it up into 256 numbers, right? Does that make sense? 0 including one of those. So we know when it's running at minimum speed, these all will be what? Zeros. And when it's running at maximum speed, these right here would be what? Would be all ones. But maximum speed, if 1,000 RPM was the maximum speed we were running, of course, then this number would equal to 1,000. So 255 would actually mean we're running at 1,000 RPM. But remember, this comes into a what? A computer. One of the main things a computer does is process information. So all you got to know is you got to know the scale, right? You'll understand. So when 255 comes in off my ADD converter, my computer would display 1,000 RPM. That's no big deal. Computers can do all types of processing of information. So the resolution of the ADD converter depends on how accurate we are, right? You understand that? So that means if I'm between a number, your ADD converter is going to either choose the next lowest or it's going to choose the next highest number. So we could have a small error. So some of our new PLCs, I don't know if I think they're 8-bit ADD converters. I'm not sure, and we need to go back. It might be 10-bit ADD converters. The new 1100 Allen Bradley PLCs we have analog inputs. But what it's going to give us, it's going to give us a number, but that number doesn't necessarily have to be the speed, right? So it's going to give us a number that represents the speed. But this is DC, and this is trying to bring DC into a computer. So you know what an A to D converter is? What does that do? Yeah, that's analog to digital. And then we have digital analog converters too. So if a computer needed to run the speed of a motor, then we're going to have to go from digital to analog. Yeah, so what we could do is we could take the output of our computer and then we could run it into a digital analog converter, and then that could actually set the speed of the motor. So what we could do is we can say, okay, I want this thing to run at 500 RPM. Well, then the program would calculate what voltage it needed to output. So this wouldn't be right. So over here I would bring in a watt. I would bring in, if it was 8 bits, I would bring in 8 bits from my computer. And then if you wanted to run at 500 RPM, then the computer would calculate what number it needed to send to the DAC to send out the right voltage to cause the motor to run at the right speed. And of course, more and more we're moving away from analog drives over to what? Computers. Because it's real neat. So now I can add touch screens. You know, so I can go up there, I want to speed up the motor a little bit, and I just have a touch screen. I can speed it up and slow it down. It shows me the exact speed up there. So, you know, we're more and more going to computers to actually do control analog devices. So DC tax. What's one of the biggest disadvantages of DC tax? For one thing, they're going to wear out.
That's why we're doing brushes.
On regular motors. So regular DC motors, you do gross meshing. So you open up the cap, you run the motor, you have that little burnishing tool you stick down in there, and you clean off the commutator, and then of course you replace the brushes. So I don't know if they have preventive maintenance, so you gotta just replace them every once in a while. Y'all had preventive maintenance.
We had preventive maintenance.
And y'all still have a lot of DC motors out there. You got to understand, DC motors, not only can we control the speed, we can control the torque. And we can go all the way from 0 up to we sling the thing apart. AC motors using what we call variable speed drives, you can only control those over a set range. So usually to start them, they'll switch them on to 60 cycle, and then when they're up and started, they'll switch them over to a variable frequency. So an AC drive will never be able to take the motor down to 0 and control the speed. Every week? I wouldn't think you would do them every week. I mean, that's on the DC generators or on the motors.
Energy sets this week, next week,
I was on brush man. That's what I did on downtime. I had my certain ways that I would do.
Yeah, you got to be real careful for those burnishing tools. You can wipe those commutators out real fast. So that's why it sounded like it was, of course, you know.
But we had what they call it, fiberglass that's in there. I didn't know it.
Yeah, the insulator between the commutator.
And we had, I don't know what that stuff was all down in there. Man, we had one of the motors that started acting crazy.
Yeah, because you burnished them so much that copper got in.
Yeah, we had General Electric them. They didn't know what they were.
Really?
You know, General Electric stuff.
We used to use a wood toothpick. You just go down between those every time we burnished it, we'd stop the motor and go through there.
That's what he said. He said, if we could have called it, we could have put something on it. But man, it was hanging out pieces of palm. This is a guy named Gary. I don't know who he was, but this guy was a farmer overseas. He worked for Gary. They sent him out and they had problems. Shit, he came in that man. He figured that thing out. It might took about a week.
So now you know you got to clean the gap between the commutators.
Who would use nitrogen?
That would work good too.
Mask on, safety glasses, you should see the crap.
Yeah, coming out of there, and you can understand why it does that. AC tags. These guys are very, very simple. So these guys here last a long time. They basically last forever. Because what they do is they spin the magnet. They don't put the magnet on the outside. The permanent magnet is what's spinning. And then you have the stationary fields that never move. So we don't have any mechanical connection between the rotor and the field. And the field.
Oh, okay. I see it. That says F/V.
Yeah, that would be what we call a frequency to voltage converter, which is not really necessarily, because what's happening with this is we got two things we can use to sense the speed off an AC tag. So what happens is as we increase the speed and combination of both tag. So that's why when we come out of the motor, we actually have 4 wires. The red and blue is the motor. The green and yellow is the tag. So what we'll do is we can come up here and spin this thing. And then we'll let y'all see what goes on with the AC tag. So what 2 things you think is going to change when I change the speed? Frequency is going to change. And what'd you say, Kathy? Amplitude. So that's the 2 things that's going to change. So on an AC tag, what we can do is we can either use the frequency. We can either use the frequency to indicate the speed, or we can do the amplitude to indicate the speed. So if we got a computer loves to count. So we could basically bring this thing in, take it from AC, convert it to a pulse waveform, which is really, really easy. Bring that right into a computer port, And then the computer, you know, while it's taking its time off, it could count those pulses without any problem. So these guys work real well with digital. And if I ran it into an analog drive, which is what this went to, all we have to do is take the AC and rectify it. And then that would turn it into what? DC, and it would vary with frequency. So let's see if the motor is going to run first. Be sure I got my colors right. But now I'm connected to the motor side. So I'm putting DC in, so DC allows me to control the speed of the motor. Of course, I can't see it because I don't have a piece of tape in it. But right now, this guy here is spinning. And then what I'm going to do now is take my oscilloscope, which shows me what's there, and hook it up to the tach generator. And then we'll look at this on our oscilloscope so we can see exactly what's going on. So this was actually the motor that used to run a 5 1/4 inch floppy disk drive. Of course, when we transfer information with a mass storage device that's rotating, and speed is very important. And this was a really reliable speed sensor. So this is my oscilloscope. I'm going too fast. I got my scope tracing too fast. So we're going to slow it down quite a bit. And then of course we're out of sync, so let me get it down here and sync it. So that's the output of the tach generator at this speed. I'm going to come over and increase the speed. Right off the bat, you should see not only is the frequency going up because the time is getting less, but also the what? The amplitude's going up. Sorry guys, one thing. And this is what's so neat about an oscilloscope. So I could take an AC meter, and I couldn't see frequency. What I could see is I could see the output of the AC varies with the what? With the speed. But not only does the amplitude vary with the speed, but also the frequency varies. So I could very easily run this into a little circuit using a single transistor that would take this and cut off the tops and the bottoms and convert this into a digital pulse stream. Very easy. So with an AC tach, we can use two things. We can either use the what? We can use the output voltage to indicate the speed, or we can use the output frequency. See, so if I slow the motor down, you'll notice that the pulses get further apart. But not only do the pulses does the waveform get further apart, also it's doing what? It's dropping down.
This is output voltage and the output
Frequency.
to
Indicate speed. So if frequency goes up, time goes down. So that's why you see them get closer together. But not only do you see them getting closer together because the frequency is going up, you also see what? The amplitude is going up because the motion is faster. Right? So this is a pretty neat little motor in that it is this is an MG set. But it's inside an MG set is a motor generator set. So we have a motor spinning a generator. This was very popular for years, especially before we really got into a solid state where we needed to change the frequency of the incoming frequency. So we had a some induction heaters over at Inslee. We called it the Curve Master, that heat treated the crown of the rails, and those induction heaters worked off 600 hertz. Well, the problem is Alabama Power didn't give us 600 hertz, right? So what did we have? We had an MG set, had a I don't know if it was an AC motor or a DC motor. It was a good size, and then they had the MG set, and they had it in nitrogen. So that was one of the motors that our motor crew, our electric shop, couldn't rebuild. So they kept a spare on hand all the time, and then when one of them went down, they'd ship it off to have it fixed. Before we left there, they changed it over to solid state. So that means we could fix it now. We'd have to ship these things off, and we could get these cabinets repaired. So this is an AC tach. These guys are used all over the place. They basically need no maintenance, right? You understand. We can seal them up really nice, run them in real harsh environments. We don't have to worry about brushes. We don't have to worry about commentators. Because like I say, what's spinning is the magnetic field. So when that magnetic field spins, we have the stator or the stationary field sitting out there doing nothing. So what we're generating, we have no slip rings in this thing, so very, very, very reliable. And if I needed DC, all I need to do is just rectify it, which is very simple. Yes and no. Now we have slip rings. We have slip rings on regulated generators. This is not a regulated generator. What a regulated generator is going to do is going to maintain the constant. It's going to maintain a constant output, no matter what the over a load range. Right? You understand that? This we don't regulate, so we can use a permanent magnet. So if you looked at the alternator on your car, so it means I can go out there and I can put a voltmeter on my car. And as long as I'm above 1,000 RPM, that sucker is going to regulate it pretty close to 14. It's going to be 14.3 in less than 15. I can turn on my air conditioner. I can roll windows. I can increase the speed of my motor. I can decrease the speed of my motor. Well, what that means is we cannot use a permanent magnet. We got to use a what? Electromagnet. So what they do is they don't want to get the load off of something that's spinning. So on the alternator, it has two slip rings that come in here, right? And then we only have one set of brushes. And then this goes over to a spinning electromagnetic field. And then up here, of course, we have the windings that we induce our voltage into. So what happens now is I can control the strength of the spinning field. So that means if my alternator voltage tries to go down, my regulator puts more current into the field, which causes the voltage to go up. To stay the same, you never even see it. If it tries to go up, it puts less current in there, which regulates. So a regulated generator will have slip rings. AC generator will have slip rings. But this is not regulated. We want this thing to change what? We want the voltage to do what? Change with speed. So what that means is I come up here and I spin a permanent magnet. And then over here I have my coils that's picking up the voltage. So now if the speed goes up, my output voltage goes up. If my speed goes down, my output voltage goes down, because that's what we're using this for. So a brushless DC motor, even a brushless DC motor, we still have to have slip rings, right? You understand? We still have to have commutators because we've got to have that very magnetic field. But an AC generator, if we don't want to regulate it, we don't have to do what? And we don't want this to be regulated. Understand, Kathy? So yeah, if I've got on my car, I could go out there and like I said, on your car alternator, it's an AC generator, right? You understand that? Sooner or later, that thing's going to go out because what's going to happen? Yeah, these brushes are going to wear out. And believe it or not, you take this generator in, you buy you a new one, pay a couple $100. They want to trade in. They go in and clean up the slip rings and put new brushes in there. That sucker's ready to go again. Probably maybe $2 or $3 worth of parts. So And they still have Chansey, I think, generators still down on 18th Street investment. So, you know, you can go in there and buy used ones, and you could take your old one in there too. They used to rebuild them for you. We have a device in here we call a photodiode. Well, we have a LED. Y'all understand what LEDs are? Oh, why won't they let me write? Oh, I know why I won't let me write, because this is off the internet. So I'll call this. So if your drive outputted, if it was a single direction drive, and it still won't let me draw. I don't know what's going on. So what we had is if we had a drive that outputted that only ran the motor in one direction, then what they would have, if this was plus and this was minus, what they would have is a big old diode in there sitting like this. So if the DC motor, if you tried to stop the DC motor, it would try to turn into a generator. The generator would be trying to work basically into a short circuit and cause the motor to actually follow the drive. So it couldn't run slower. It couldn't run slower than the drive because it speeded up. But if it tried to run faster than the drive, it would try to turn into a generator. That diode would forward bias. It would be working into a short circuit, and it would cause it to track the drive. And we did the same thing on drives that run in multiple directions. So down here, this would be a minus and this would be a plus. And what they would do is, of course, on this one, this diode would be right here. So out at number 4 of our galvanized line, we have what we call a six-legged bucket, which was not only means you could run the drive in one forward or reverse, and then they have what they call a three-legged bucket, which was a three-line drive. Number of legs, of course, was the number of SCRs that we used. But both drives, each drive, the one that ran it in one direction, it would have its counter EMF diode. The one that ran in the other direction would have its counter. Y'all understand? So the DC motor could not turn into a generator. So it made it track the drive, so the drive could run at any speed. So even though you had that thing running a big old load and you tried to slow it down, if you didn't make it track the drive, the motor would just do what? It turned into a generator, so, which is pretty neat. So we have what we call dynamic braking. Instead of using a diode, we use resistors, and that way you can actually brake it according. And so that's what trains use. So trains, the only time they ever engage those air brakes is when they want to do what? Stop. Besides that, they use dynamic braking of AC motors. By the way, you can dynamic brake AC motors, which is pretty neat. So what you do is you take the AC away from the stator and you put DC on it, and then it turns into then you got this thing spinning, right? You understand? And what they do is they have slip rings on the armature for dynamic braking. Then they run that into resistors and they dynamic brake AC motors, which is pretty neat. So y'all can look that up. So that's it on our speed sensors. So what do we have? We have the rotary tooth sensor, which has been around for years. Then we have the tacks. We have both a lot. AC tack and a DC tack. And then we have these incremental encoders. All these guys are just use photoelectric cells. It spins through there. We make and break, and then we use the frequency coming off to indicate the speed. So any questions on this? So I'm not really sure I don't think the manufacturing line over there, or even the Festo line, has any speed regulation on the motors. All they're doing is depending on them to run at a certain speed, and then of course if we run it through a gearbox. But if you get into manufacturing, where you got to do things at a certain rate, right? You understand? You can't run them too high, you can't run them too slow. So I was looking at a video the other day where they were trying to freeze something, and basically it ran through a spiraling conveyor belt, and they had to make it go through there for a certain amount of time. Well, if you're going to make it go through there for a certain amount of time, then what does that mean? Yeah, you're going to have to run those belts at a precise speed. On number 4 galvanized line, I know I talked about that, but that was one of the most modern mills when I was out there. They were running that strip through an oven. To get metals to bond, you need to have those two metals at the same temperature. So what they did is they ran that strip through a furnace, which heated up the tin. And by George, to get that thing at the right temperature, well, they had to do what? Not only did the furnace have to be at a certain temperature, but they had also had to send that thing through there at what? The right speed. And then, of course, they'd take that hot strip and they would run it through the zinc. The zinc was heated up, you know, it's melted. They were pretty much about the same temperature. And what did they do? They bonded. Anybody that understands soldering, that's what you do. You don't solder with the torch. What you do is you use the torch or the iron to heat up the metals. And then you use the metals to melt your solder. So if you ever did any soldering on pipes and put the solder inside the torch and did that, odds are you're going to get a lot of water leaks. In electronics, if you do that, you're going to get a lot of what we call cold solder tones. So that's to get those two metals to bond together. You want both metals to be heated at basically the same temperature. And then what happens is the molecules of the third metal or the other metal bonds with the surface molecules of the other ones, and then you'll have a really, really good bond.
The dual line, you know, that was it's the same line. They just advanced it so it takes less people.
So it's a galvanized line?
Yeah. It took less people.
But they moved it away from that.
It left from the entry end and went up in the furnace.
Went across the top.
Across the top. Once it came out of the front, it dropped down.
Dropped down into the zinc bag.
Into the zinc bag, and then it went straight back up.
Then it went through what they call a spangler, which was a big old thing that blew air, and just wanted to put those real beautiful patterns in.
And you can see stuff just fall right back off on water, right back into the thing. And then when it got up there, and dried and all that, went through all the different accumulators.
Sounds like the same line.
Same line. Then when we got down to the end,
well, first of all, what they did, they ran it through acid baths. I guess they do that first. They take the strip and run it through these cleansers to get all of the residue of it.
Well, that's what the quick line was, I guess.
I guess, yeah, but they did that at the number 4 galvanized line. They did the whole thing. So they had all those acid baths down there that the strip would run through to clean it off real well before it went up through the oven.
It went from quick line to cold mill, then to the
cold roll mill is where they set the gauge, right?
Right. Then we do it. We just put that stuff. We just call it pigs. Drop them over, big old rocks in there. Down
into the zinc.
Yeah.
Number 4 galvanized line. They didn't use the big old pigs. They used the one.
They were like this.
Oh, really?
You had to use frame.
I was up at Reynolds Metal, and they was talking about the pig farm. We need to go out to the pig farm. And they said, "You want to see the pig farm?" And I said, "Yeah." They gave me that thing, and all it was these big old crushed things of aluminum out there that they were melting down, and that's what they call them pigs. But they
you ever heard of what they used to call here, 80 or 90, something like that? You ever heard of that?
I don't know.
It's just a place, man, out there in the field where they was throwing all these old drives and stuff like that. Somebody, man, go to here, 80. Just right out there. It's flat. They go here, just flat surfing. Some of these called here, 80.
We used to go over there and run around on where they stored all the ore out there. You know, the ore that they bought was in like marbles. And we'd take our truck out there and we'd rip around on that thing. We'd be sliding all over the place, running over things. Then we'd go over to Inslee when it was shut down and go into those big old silos over there and hunt for birds with slingshots. Oh, really? So, guys, Any questions? So far we've gone over what? We've gone over position sensors. We've gone over what? Proximity sensors. We've gone over speed sensors. Of course, you can see the other lectures, and we're going to have to. Looks like we've kind of got behind. By the way, our modules are here, but we're going to have to figure out what they're doing. So the modules we have over there is we have solid state limit switches. Now, whether it's inductive or capacitive, I'm not sure. I'm almost sure it's inductive. We have liquid level switches. We have temperature switches. We have pressure switches. And then we have a photoelectric switch. So what we need to do is, we've got the labs, but we ended up using 5 stations for, we ended up using 5 stations for motor codes. We have one station that we're trying to get the parts to reuse. So what that means is we have 2 stations that's going to be available to us to do these labs. So what that means is we'll probably have to do a group of 4 and 3. They send us the labs, but the problem is that the way they send them is they're supposed to be incorporated into a motor control. So what I'm going to do is I'm going to call and see if they can, it won't be anything to y'all, but what I'm going to do is call and see if we can copy these, and then because we don't have enough sets and it's not available in book form, and then we'll see if they can in the next classes if they can put it into book form. So right now we should be able to go over there and do the layouts on what proximity, and we need to and I've been, like I said, this is the brand new course that we're kind of playing it by. We're learning as we go. We need to come up with some way, and I know y'all done 2 labs, right? First lab y'all did was the what? Was the potentiometers. Then the second lab that we did was what? Well, that was the first lab. That was all doing the transfer function. So these were the degrees that we were using for our potentiometer, and we did the transfer function for that. Right? We were trying to figure out what voltage you get at 6 different degrees. And then what was the next lab we did? Yeah, we did it. We just got through doing. Yeah, we're going to. Oh wait.
Started on the trouble part.
I'm not really sure. We have another course as part of the. And that's what I got to figure out. We got another course as part of the Siemens certification called troubleshooting. So I'm not really sure how much troubleshooting we should put in this class. Does that make sense? Because what we're looking at here, of course, is the operation of a sensor. So I'm not really sure. Like I said, we're going to have to get together and just actually figure out how these courses are going to lay out. So we still got to do. Yeah, so I've uploaded all the individual PowerPoints. So we just did the speed sensor. We have load sensors, of course. What is load going to give us? It's going to give us weight. Then we have pressure sensors, temperature sensors, flow sensors, distance sensors, vision sensors, which could also be incorporated on up here. And so these are the sensors that we're trying to cover in this class. So we still have, and we're setting where? Yeah. Of course, next week is midterm. So what we're going to have to do is figure out how we're going to do these labs. So we do have over there. We don't have load sensors. I'm not really sure what we need to do about speed sensors. I don't know how we could do a lab. You can see the Of course, we could do a lab with these. We got plenty of these little motors. We could do that. We could probably set up a lab on those. Load sensors. There's several things we can use to sense load, and we'll look at that. And we could do a lab on that. It's just that the load sensors that we would make would be extremely accurate. We do have pressure sensors, but we got to figure out what to do with those because guess what they need? They need pressure. So we do have some compressors in here that's available to us. Temperature sensors. We got no problem there because we have these paint stripper things that we use to do heat shrink. So we could definitely have no problem with heat there. Flow sensors. We don't have any labs on those, but we do have level sensors over there. We have some liquid level sensors which are pretty neat. And of course, they deal with control, so we'll have to have control circuits to come up and do those. So over there, we can do what? We can do what? Proximity sensors. Okay. We can do what? We can do pressure sensors. We can do temperature, and we can do level. And what we have is liquid level sensors over there. And we can do that over in 210. We do have a camera over there. I got to figure out how to use it. It's pretty neat. We have two cameras on our two robots. We have one on the ABB and we have one on the Motorman. But we also have a camera that's not mounted on the line over there. They said we could figure out how to mount it and what we wanted to do, but that's going to be very interesting. But I guess that's it. So what do we want to do? So what I'm going to do is I'm going to run these labs off for you. So we already have the lab on proximity sensors. There's 3 experiments inside the section. Y'all have had motor control, right? So these are laid out the same way. It's laid out in chapters. So what I've done is I've ran off or scanned the section on proximity sensors. So the first part, I think the first lab is on solid state sensor, and then the next part is on the photoelectric sensor. The photoelectric sensor over there looks like it's a retroreflective sensor. So it's got the retroreflectors that come along with that. And of course, I haven't looked at the lab, so y'all have to help me figure out and see if there's going to have to be any modifications made. So what we'll do Thursday, what do y'all want to do? Let's just go ahead. So let's don't really do any troubleshooting on this class, okay? Because like I said, we got plenty of material to take us through the entire term. So what we'll do Thursday is we'll just meet over in 210. Everybody okay? Huh? Yeah, motor control. And that's what our sensors are set up for. They're set up for motor control. So, but what we'll have to do is we'll have to include other things. So we have a sensor, but it's going to be part of a control circuit, right? Does that make sense? So that's why we're going to require that people that take this class, they're going to have motor controls first. I think that's a good one. So okay. So where we're going to meet Thursday? I'll try to remember to put a sign on the door, but if you come in here and the door's locked, it should come up and say, well, oh, where's everybody at?